Hi guys, my name is Zahira. My metric number is 227748. So now I want to talk about the ordinary differential equation, or we call it as ODE. So what is ODE actually? ODE is an equation which involves one or more functions of a single independent variable and its derivative. So guys, bear in mind, ordinary differential equation contain only one independent variable. Compared to the partial differential equation contain more than one independent variable. So have you heard about the Newton's second law of motion? As you guys know, the formula of the Newton's second law of motion is F equal to ma, whereby F equal to force, m equal to mass, and a stands for acceleration. So where is the ordinary differential equation in this formula? Basically, if we go through the formula, we can break down the acceleration. I'm sure you guys have heard about this formula. This formula explains about if you guys differentiate the displacement, you can get the velocity, and if you differentiate the velocity, you can get the acceleration. In this formula, we can break down to the F equal to m times with dv over dt. Then we can also break down into the second derivative of distance, which is d square x over dt square. So here we get the F equal to m times with the second derivative of distance, which is equal to acceleration. So where is the ordinary differential equation in this formula, which is d square x over dt square? The independent variable is t, which stands for the time, because changes in t will determine the changes in x. So this equation is an ODE, which is ordinary differential equation, because it involves a function and its derivative with a single independent variable. That's all. Bye!
My name is Shirley Tin Fong from Group A. Today I want to discuss about a partial differential equation. So what is a partial differential equation? PDE is a differential equation containing partial derivatives of the dependent variable one or more with more than one independent variable. PDE commonly used in physics or engineering areas such as heat equation. The heat equation given here arises from the principle of heat conduction and thermodynamics, which are governed by Fourier law of heat conduction and the conservation of energy. Why I say this equation is a PDE? Because in this equation, Ux, y, t is the unknown function representing the temperature. It has derivatives with respect to both space x, y, and time t, meaning it depends on multiple independent variables. Now I will show the steps how to convert this with physical laws into a PDE. Step 1. Fourier law of heat conduction. That is the equation given. Step 2. Conservation of energy, heat balance equation. Using the divergence theorem, the net heat flow into a unit volume is shown by the shown. This represents how heat flows within the material. Step 3. Applying the first law of thermodynamics. Step 4. Deriving the heat equation. So, the heat equation is derived as a PDE from fundamental principle of heat conduction and energy conservation. It is a parabolic second-order PDE, widely used in engineering, physics, and material science to model heat distribution over time.
Hi, my name is Putri Alia Kistana binti Muhammad. My metric number is 231049. So today, I will briefly explain about linear differential equation and also nonlinear differential equation. These equations are essential in mathematics, physics, and engineering because they describe how quantities change over time or space. So, for the first one, definition of the linear differential equation is an equation that involves a function and its derivative, where the function and its derivative appear to the first power and are not multiplied together. I provide the general form as you can see here, and a nonlinear differential equation is an equation where the dependent variable or its derivative appear with exponents other than 1 or multiplied together. Unlike linear equations, this equation often exhibit more complex behaviors such as chaos and bifurcations. The general form does not have a strict structure like linear equation, but also includes terms. So for the applications, linear differential equation and also nonlinear differential equation are widely used in real-life applications such as modeling electric circuits, fluid flow, mechanical vibrations, and also economic systems. So the conclusion is, in summary, linear differential equation and nonlinear differential equation are powerful tools that help us analyze and predict various natural and engineered systems. Understanding their solution is key to solving real-world problems.
Hi and Assalamualaikum. My name is Amar Khairina binti Azmi and my matrix number is 230566. Okay, in my part, I'm gonna present about differential equation that focusing on two cases, which is homogeneous and non-homogeneous. Okay, on this slide you can see two equations, which is general equation and homogeneous equation. I'm not provide the non-homogeneous because the equation seems like general equation, but the difference is for general, the equivalent can be non-zero and zero, but for non-homogeneous, the equivalent must be non-zero. So if you can see here, A, B, and C is a coefficient that might be constant or change over the time. And Ft represent the external influence acting on system. If Ft equal to 0, the system involved is outside the interference. So if you can see the homogeneous, the equivalent is 0 because there's no external force that acting on the system. So this is equation for a free fall situation. So if you can see here, M is represent for mass of the ball because I'm using ball as an object. D square y over dt square is the acceleration of the ball, while g is the acceleration due to gravity, and we use a 9.8 meter per second square. This is not homogeneous. The difference just we add the negative kV, which is the force due to air resistance, where K is constant that represent air resistance. So basically, non-homogeneous, they have external force inside, such as air resistance. Okay, if you can see here, I provide an example for free fall with air resistance and without air resistance. For free fall with air resistance, this is for non-homogeneous. If we drop the ball at the same atmosphere where the air is slowed down, the equation become kV that I show in the first slide. So that mean there is air resistance involved in situation. So for without air resistance, imagine we drop the ball from high in the vacuum. There's no air resistance. The only force acting on it is just gravity. So there's no external force beside gravity. So this is a homogeneous equation because equivalent is equal to 0.
Assalamualaikum and hi everyone. My name is Nurul Aiman Naziratulina binti Norman. My matrix number is 229270, and today we're going to talk about a differential equation.
So the case study that I've chose is a radioactive decay equation, where as you can see there, the equation is dN over dt equals to negative lambda n in a bracket of t, where n is the amount of radioactive substance remain and t is equal to time,
dn over dt is equal to the rate of change of the substance with the respect to time. The lambda is equal to the decay constant, and the negative sign is indicate the amount of substance decreasing over time. Okay, let's classify the equation. So for the classifications of this equation, it goes below the order of differential equations, where this equation is the first order of differential equation since it's involved the first derivative of dn over dt with the respect with time. This equation also is a homogeneous differential equation since all terms in the equations involve the dependent variable and there is no external forcing term. And this equation also a separable equation since this ODE can be solved by separating variable leading to the general equation. So this is the general equation that I've been talking about. So how can we get the general equation? By solving the differential equation. Since the equation is separable, we can separate the variable and in bracket of t and t. Then we can integrate both sides. By integrating both sides, we got ln modulus n in the bracket of t equals to negative lambda p plus c, where c is the constant, and then we exponential this equation, and then we get n in the bracket of t equals to n naught exponential to the power of negative lambda t. So that is the general equation for this radioactive equation. And that is all. Thank you.